Good morning, students. In the earlier video, we have discussed the modes of transfer of charge. So I explained you three modes of transfer of charge. First was friction, that is by rubbing. We can transfer the charge from one body to the another by rubbing them. Then by conduction, what happened in conduction? When a charged body comes into contact with another body which is having charge or uncharged, then some charge between the bodies get interchanged. Then the third was by induction. In induction, the physical contact is not required, and the charge appear on the another body was different in the nature as the parent body. Then we have studied the properties of charges. So although we have some more property, but these properties are important. First, that alike charges repel and unlike charges always attract each other. Then we have conservation of charge, and what was in the conservation of charge, that charge neither be created nor be destroyed. It can be only transferred from one body to the another body. It means that total amount of charge present in the universe remains constant. It's like an energy. Then quantization of charge. Quantization of charge explain that we can transfer charge from one body to the another body only in the multiple integral of E. And what was E? E was the charge of electron, that was 1.6 into 10 to the power minus 19 Coulomb. Then invariance of charge. It means that charge does not change its value when it starts moving, unlike the mass, because the mass of the body changes when it starts moving, but it doesn't happen with the charge. These are some important properties of charges. Now we'll study some more phenomena of the charge, like as I discussed that two charges attract or repel each other, but what is the value of the force of attraction or repulsion? There must be some value. There must be some magnitude. So what is the magnitude? How we can calculate it? What is the unit of charge? What happened if the two charges are placed in air or in vacuum or in some material medium? How the force between them affected? Let's talk about the unit of charge. The SI unit of charge is Coulomb. It names after the scientist Coulomb because he gives a very important Coulomb's law. We'll just study after some time. So SI unit of charge is Coulomb. Now we can define Coulomb in the terms of ampere also. We know that current is nothing but it is equals to charge upon time. That is, we know that the definition of current, it is nothing but rate of change of charge. It is the rate of charge flowing in a circuit. So from here we can write the charge equals to current into time charge. As I discussed, the unit of charge will be Coulomb. So 1 Coulomb equals to the SI unit of current is ampere. You know that ampere is one of the 7 fundamental units. So 1 ampere into 1 second. So this is the relation between Coulomb, ampere and second. We can define 1 Coulomb as if a conductor carries a current of 1 ampere for 1 second, then the charge that flows through the conductor will be 1 Coulomb. See, you don't have to memorize this definition, you can make it by this formula. How? 1 Coulomb charge will be flow in the circuit if the 1 ampere current flows for 1 second. That means that the amount of charge that transferred in the body is 1 Coulomb. Let us discuss the Coulomb's law. Coulomb's law basically used to calculate the force acting between two or more charges placed in any medium or in vacuum. This law is like gravitational law, that Newton's law of gravitation. The only difference between these two laws is in gravitation we use two masses, but here we use charges. Gravitation force was due to the mass, but here the Coulomb's force, or we can say electrostatic force, is due to the charge present in the body. So let's see what is the Coulomb force, Coulomb's law. Let us talk about first the force between 2-point charges. We'll discuss how it acts between more than two charges later, but let's see the first basic case, the force between 2-point charges. Let us compare this force with gravitation. As I told you that this force is quite similar to the gravitation. So I discuss the gravitation law here. What was the gravitation law? It says, suppose we have two masses, 2-point masses, having masses m1 and m2, and they are at some distance r. So the force of attraction between these two masses was directly proportional to the product of their masses and inversely proportional to the square between them. Inversely proportional to distance of square between them. So if we combine them, we'll get m1 m2 upon r square. So in the place of this proportionality, we've applied the constant, which is g. So F equals to g m1 m2 upon r square. This was the gravitation law. Now let's talk about the Coulomb's law. Suppose we have two charges. These are two charges having magnitude q1 and q2, and they are at distance r. And now suppose they are placed in vacuum or in air. Now according to Coulomb's law, force between them is directly proportional to the product of their charges. Here it was mass, and in the Coulomb law we have charges, and the force is inversely proportional to the square of distance between them. You can see it's quite similar. If we combine these two laws, that this is the equation number 1 and this is equation number 2, So F will be equals to Q1 Q2 upon R square, and in the place of this proportionality we will apply a constant which is equals to 1 upon 4 pi epsilon naught Q1 Q2 upon R square. So this becomes a formula for electrostatic force between the two charges. It can be repulsive, it can be attractive depending upon the nature of charges. Now the constant was 1 upon 4 pi epsilon naught. Now what is the value of constant here? Like in the gravitational law, G was the constant whose value is 6.67 into 10 to the power minus 11 Newton meter square per kg square. Now here the value of this constant is 9 into 10 to the power 9. But you know that we never write anything physics without unit. If this quantity have some unit, we must show it. So what is the unit? It is Newton meter square per Coulomb square. So this is the value and unit of the particular constant. Now let's see what is the dimensional formula of this particular constant. How we can calculate? We see here it is Newton, then meter square, then Coulomb square. We can find the dimensional formula separately. Newton, that means force. So for force we know that the formula is mlt minus 2, and for meter yani ki length, for length it is basically L, and for Coulomb is nothing but charge. So what was charge? Charge was current into time. So current, that means ampere, we can write A, and for time we can write T. So for Newton we get mlt minus 2, for meter that is L, for charge that is current into time AT. Apply here, so we'll get mlt minus 2 L square upon AT square. When you solve it, you'll get m L cube T minus 4 A minus 2. So this is the dimensional formula for the constant 1 upon 4 pi epsilon naught. Now what is the value of epsilon naught here, and what it's known as? Here epsilon naught, it is known as permittivity of free space, and the value of epsilon naught is 8.85 into 10 to the power minus 12. Again, unit is important. So the unit is Coulomb square per Newton meter square. Again, we can find the dimensional formula for epsilon naught. Coulomb, that is AT, it will be A T square divided by mlt minus 2 and L square, which gives m minus 1 L minus 3 T4 and A square. So this is the dimensional formula for epsilon naught, which is known as permittivity of free space. See, basically permittivity of any medium is responsible for the magnitude of force of attraction or repulsion between the charges. Like it's like the property of medium. Like in in the light chapter, you know that the amount of deviation of light depends upon the refractive index. More the refractive index, more will be the bending of light. Similarly, the magnitude of the force of attraction or repulsion between two charges, it depends upon the permittivity of permittivity of that medium. So we'll apply this epsilon naught here, epsilon naught only when the charges are placed in vacuum, because you can see here epsilon naught is the permittivity of free space. It can be used for air as well, but we can't use this epsilon naught for any other medium. What does it mean? It means that if the charges are placed in any other medium, then the value of this constant will be changed. We'll apply this formula, this constant, only when the charges are placed in vacuum or in air. So what happened if the charges are not in vacuum or in air? They are placed in some other medium, like they are placed in wax or in oil or in any medium. Then what will be the change? What will be the new value of this constant? So now let's assume these charges are not placed in vacuum or in air, rather than they are placed in some medium. Now using the epsilon naught, we use only epsilon. For example, if the charges are placed in medium, then the formula will be, and I'm showing it with f dash, it will be 1 upon 4 pi epsilon, not epsilon naught, only epsilon, q1 q2 upon r square. Now what is epsilon here? Epsilon is known as permittivity of medium. So for example, that in the air we use epsilon naught, that was permittivity of free space, but now here we are taking permittivity of medium. Now what is the value of permittivity of medium? It is equals to epsilon naught into k. What is k here now? K is known as dielectric constant. K is dielectric constant. The value of dielectric constant is different for different medium. It is always given in the question. If some question comes in your paper that the two charges are placed in some medium, then there must be the value of k. They'll give the value of k. So if here we apply the value of epsilon, what we'll get? We'll get f dash is equals to 1 upon 4 pi epsilon naught k q1 q2 upon r square. You can observe one thing, that if the system is placed in vacuum or air, then there will be no k here. It means that the value of k, that means dielectric constant for vacuum or air, is 1. K is equals to 1 for air and vacuum, right? So in comparison with the force in vacuum and in the medium, F dash will be F upon K, because we know that F was equals to 1 upon 4 pi epsilon naught Q1 Q2 upon R square, but in F dash they were the division of K. There's an important note I am writing here, that if there is some dielectric between the charges, then the force between them decreases by factor K. It means for all dielectrics the value of K is greater than 1. What is dielectric? Basically dielectric is nothing but they are simply insulators. For all dielectrics, the value of K is greater than 1. So this was your Coulomb's law. In the next video we will discuss how we'll solve the numerical, those are based on the Coulomb's law, and how we can apply this law when we have more than 2 charges. So there are some numerical problems in your notebook, you can try them, and if you have doubt, even you can ask me. Thank you so much for